tetrasubstituted alkene. So you don't have any CsP2H. So we don't have, which are, in this case, you have only signals below 3000. So to the right, not to the left. In this case, you have CsP hybridized carbon atoms, two atoms. But again, you have a disubstituted. No, we have we could say in this case internal. We say internal alkyne. Sorry. So you don't have any CsPH, and therefore you cannot see any signals above 3000. Understand this?
Sorry, but your microphone is turning off.
Really? Okay. That's why no one answer me. Okay. Okay, I will check it. Hello.
We hear you.
Em nghe được.
Thế sau đấy đạt lại bảo là tắt nhỉ? Nên nghe được rồi đúng không em? Yeah. Nhưng mà các bạn có thể thấy thầy vẽ ở trên cái slide không?
Có.
Okay. Và chúng ta thấy đồng ý với những cái phân tích đấy đúng không? Okay. Okay. Okay, in compound D, you have an CsP2 hybridized carbon atoms, and therefore this will absorb light at wave number of 3100 centimeters to the -1. So on the left, here you also have a tetrasubstituted. Tetrasubstituted alkenes, or in other words, you don't have any CsP2H, so you have in this case only a signal below 3000. Ở đầu bài tôi hỏi là on the left of 3000 có nghĩa là có tín hiệu ở trên 3000 không ấy, các bạn hiểu không? Yeah. On the left nghĩa là tức là bên này đây là on the left này. Còn đây là on the right. Và cái vùng 3000 là liên quan đến CH bond. Yeah. Okay. So the last one, you have a terminal alkyne. So terminal alkyne has one CsPH bond. So you see it somewhere at 3300 centimeters to the -1. So this is this part just a review about the absorption of CH bond in the infrared spectrum. Okay. Okay, so each of the following compounds contains 2 carbonyl groups. Identify which carbonyl groups will exhibit signals at lower wave number. Okay, so this exercise is to review about saturated and unsaturated conjugated carbonyl compound. So if you remember saturated carbonyl, saturated ketones have these structures. Yeah? It does not have any double bond next to the carbonyl group. And then you have unsaturated conjugated ketones. Then in this case, you have a CC double bond in conjugation with a CO double bond. My picture is so bad. So I make another one. So this is the conjugated system. And if you remember, we use resonance structures in order to compare or to explain for the difference between the wave number of these two kind of carbonyl compound. So if you remember, the saturated carbonyl group will absorb at high wave numbers, 1,740 centimeters to the -1. But the carbonyls in unsaturated and conjugated ketones will absorb at about 60 centimeters to the -1 lower than the that of the saturated ketones. And now in this exercise, you just identify these two kind of ketones. Unsaturated and conjugated ketones are those that have a CC double bond, and that is one bond separated from the CO double bond, one bond apart. So A is one example, right? So this is an unsaturated. This is a unsaturated conjugated part. And this is a saturated ketone part. So this one, the saturated one, will absorb at about and the unsaturated and conjugated part will absorb at. So if you take this compound and you put it in between two potassium bromide salt plate, and you radiate the sample with infrared light, then you get a spectrum in which you see two different signals corresponding to two different kinds of carbonyl groups. One is saturated and the other is unsaturated and conjugated carbonyl functional group. Okay. In structure B, you have also, this is an unsaturated sorry, I think this just 20 for ketones, unsaturated and conjugated Now it is not a ketone, but it is an ester. And esters will absorb a little bit higher than ketones. So it is 1,740 centimeters to the -1. No. I think wrong. 1,740 is for this one. Yeah, for the saturated. No, sorry. Yeah. And for the unsaturated conjugated, what is this? What is the number of this? What is the what? For unsaturated conjugated, it should be a little bit lower. So what is the value for unsaturated? Give me a number. Yeah, one. Yeah. Right. So you start to remember better than me, right? Okay. In the last structure, you have two different kind of ketones. Two different kind of carbonyl. The first one is in ketones, a saturated ketones, and the second carbonyl group is in unsaturated esters. So this one should be 20 centimeters to the -1, and for ketone is about, for ester is about, yeah. Okay. Reviewed about the carbonyl group. The wave number of the absorption wave number of a ketone, a carbonyl group can be different if it is in a ketone, a saturated ketone, unsaturated conjugated ketone, or in an esters. So you can use infrared to might identify this kind of carbonyl functional group. Okay. Compare the wave number of absorption for the following CC double bonds. In this, in our previous section, we have compared saturated ketone and with unsaturated conjugated ketones. Now you compare the CC double bond in the isolated, we say in this case, isolated CC double bond. We say isolated because it is 2 sigma bond away from the CO double bond, no conjugation. And in this case, the CC double bond and the CO double bond are in a conjugated system. So you see that they have different absorption wave number. And again, the unsaturated conjugated is at lower wave number. Now you have to draw the resonance structures. And with this CC double bond, actually you can draw in both ways. So like this, or you can draw in the other way around. You can place the positive charge right here and the negative right there. So you have two different kind of resonance structures. And for this, actually you will draw resonance structures like this. Okay, I will draw it slowly, more slowly. Yeah, I will do it like this. So this is first, and then you have the second. I miss a positive charge there. Actually, I can draw another's resonance structures like this. Yeah. So actually on the right structure, you have 4 different resonance structures, and on the left, you have 3. So please tell me about the meanings of these resonance structures. What do these resonance structures tell you? First, you have to evaluate the contribution of each resonance structure to the real structure of the compound. So do you think that they are important or not important? They contribute much or little? So I think these 2 resonance structures are very unstable, because you see that you always have a positive charge on carbons. Positive charge on carbon indicates that it has an incomplete octet. It does not have a full Aufenthaltschaft. Yeah. And the same for all this. But it is even worse, because you always see that a negative charge on carbon atoms. You know that the electronegativity of carbon atoms is medium. And carbon atom therefore does not have the good abilities to store a negative charge. The same for this, something is the same for this. So better. This is a little bit better, because you also have positive charge on carbon, so not full octet shell. But in these structures, this one, you see that the negative charge is on oxygen, whose electronegativity is large, is great, high. So this one is good, is okay. That could you can turn off your camera. That you can turn off your camera. Hello. That could you you can turn off your camera, please. Okay, you do understand what are we doing? Okay, do you understand what we are talking about? Hello. Do you understand what we are discussing about? Okay, so which structures is which of the resonance structures contribute much to the real structures? So this one contribute much to the real structures. So you see that in this structure, the CC bond has some more single bond properties. And therefore its absorption wave number is lower. And this has higher double bond properties. Single bond property. Okay. Okay. So you can take notes about this and can have a look again at home by yourself. Okay. So in the next section, we will discuss about the next parameters of signals in infrared spectrums, intensities, and we would analyze factors that influence these properties. Okay, in an infrared spectrum, some signals will be very strong in comparison with other signals on the spectrums. So in this picture, you see two signals. Yeah? The first one on the right, it is small triangles. I said a small triangle because it has a small head. Yeah, small head. We imagine that each peak is a triangle, and this one has a small head. On the other hand, this one on the left has great head. So you can guess that the triangle on the left will have a greater areas. So strong signal means great areas. And this one, because it has a small head, so it will have a small area. Area là gì các bạn nhỉ? Yes. Vậy thì tam giác. Một cái tam giác của mình, một cái tam giác của mình là cái đáy đúng không? Base đúng không? Và hết đúng không? Thế thì cái base của hai cái này có thể coi nó như bằng nhau đúng không? Base là cái này đúng không? Nhưng mà head, yes, so it depends on both factors, head and base. In this case, the base of the two peaks are quite similar, so we compare just the head. Height, oh, sorry, height. So you don't understand what I pronounce. Okay. Okay, I always pronounce this as head from 5 years old till now. Okay, so I will have to correct it as height. Okay, thank you. Okay, so we compare the height of these two peaks, and you see that the one on the left is greater, and therefore you have a greater areas. Greater area means strong signals, yeah, and small area means weak signals. Okay. So strong signal means that bond absorbs infrared radiation very efficiently, and weak signal means that bond will absorb less efficiently at that wave numbers. Okay, So to understand why there is this difference, we must consider how the strength of a dipole moment change when a bond vibrates. So if you remember from organic chemistry 1, the dipole moment is the property of a bond, and it is defined by the charge multiplied with distance. The letter E in this case is the strength of the partial charges, delta plus or delta minus, and D is the distance between these two charges. So what happens to the strength of the dipole moment as a bond stretches? So when a bond stretches, when the bond vibrates or a bond stretch, the distance between the two charge centers is constantly changing. So the strength of the dipole moments also change with time. So you see that there is a plot of the dipole moment as the function of times showing the oscillating dipole moment. Yeah. So it changes with times. And the dipole moment is an electric field surrounding the bond. And when the dipole moment oscillates, the bond is essentially surrounded by an oscillating electric field. This electric field serves as an antennas for absorbing infrared radiations. And if you remember, electromagnetic radiation itself is comprised of an oscillating electric field. So the bond can absorb photons because the bond's oscillating electric field interacts with the oscillating electric field of the infrared radiation. And therefore, the efficiency of the bond at absorbing infrared radiations depends on the strength of the dipole moment of that bond. For examples, so the efficiency of the bond at absorbing infrared radiations change with its dipole moment. We can say the higher the dipole moment, the greater the dipole moment, the more efficiently that bond will absorb infrared radiation. Okay, so we have an examples. You see two double bonds. One is CC double bond and the other is CO double bond. They are both double bond, but if you measure their dipole moment, they will have different values. Due to resonance and induction, the carbon atoms of the carbonyl group will have a very clear, very significant partial positive charge, while the oxygen atoms have a significant partial negative charge. And therefore, the carbonyl group will have large dipole moment. It is different when you look at the CC double bond. The vinylic position is connected to an alkyl group, and the other vinylic position is connected to hydrogen atoms. So if you remember, we have this is the vinylic position. This is the vinylic position, and the first vinylic position is connected with two different hydrogen atoms. And the second vinylic position is now connected with two alkyl group. This is an alkyl group. And you remember that the CH bond and the CC bond are not polar bond. CH and CC bond are just covalent bond. And here you have polar covalent. And so the two vinyl positions are not electronically identical. So there will be a very small dipole moment. And you can see the diagram, the plot for the dipole moment depending on time of carbonyl and CC double bond. So the dipole moment of the CC double bond changes very little with times. And on the other hand, the dipole moment of the carbonyl changes with a large range with times. So the oscillating electric field associated with the carbonyl group is much stronger than the oscillating electric field associated with the CC double bond. And therefore, the carbonyl group will absorb infrared radiation more efficiently. And it is shown as a stronger signals. Stronger signal means larger areas of the peak. Okay. So these pictures is a comparisons of the intensities of the signals arising from a CO bond, double bond and a CC double bond. So you see that now you have really two different triangles in terms of both height and base. Yeah. So you see that the base of CO peak is significant greater than the base of the peak of CC double bond, and the head, the head of the CO double bond, the peak of CO double bond is nearly 2 times greater than that of the CC, the peak of the CC double bond. And in this case, we said the CO double bond have a stronger intensities. And in fact, the carbonyl groups often produce the strongest signals in an infrared spectrum, and while the CC bonds produce weak or medium. Some alkenes even don't produce any CC signals at all, because if the structure is symmetric, then the dipole moment is very small. So for examples, this is the infrared spectrum of 2,3-dimethyl group 2-ene. The structure is completely symmetrical, and therefore the dipole moment of the CC double bond is, let's say, nearly 0, and therefore you see nearly nothing at the region of 1 1,680 centimeters, nearly nothing. This is the range for the absorption wave number of CC double bond. But you see here nearly nothing because of the small dipole moment of these structures. This alkene is nearly symmetric, is almost symmetrical. So it will possess a very small dipole moment. Okay, so remember that symmetrical CC double bond are inefficient in absorbing infrared radiations. And in that case, in those cases, you may not see the signal for CC double bond. Tất cả những cái này giải thích này có thể mình cũng chẳng cần nhớ gì cả, mình chỉ cần biết là nếu nó đối xứng thì nó sẽ không có tín hiệu được thôi. Gần đối xứng thì tín hiệu yếu, còn rất không đối xứng thì tín hiệu mạnh hơn. Okay, the same is true for symmetrical CC triple bonds. So in this slide, you see the infrared spectrum of an alkene. In this case, a terminal alkene, oct 1 ion. And the most prominent absorptions in the spectrums are the followings. So you see signals at 3,313 centimeters to the -1, far away from 3,000. So it corresponds to the absorption wave number of CSPH at the terminal of the alkyd. And the second is also a sharp and weak at about 2,120s. And the first one, this one. I'm sorry, this one, quite strong. And the second is for CC triple bond. But when you analyze the spectrum of an internal alkyd, an internal alkyd will have a CC triple bond in the middle of the main chain. So in this case, no signals for no CSPH bonds. So of course you don't see any signals at the range of 3,300 centimeters. No signals because you don't have CSPH. And also in the range of about 2,100, you don't see signals or very weak signal for CC triple bond because this structures is also symmetrical. And symmetricals will have a small dipole moment, and small dipole moment will change a little, very little with times. So it cannot be a good antenna for the infrared radiation. It absorbs radiation inefficiently. Okay, so I think we have should have a short break. Yeah. Okay.